Good morning and welcome to session 5 of the FoRRRwD webinar. It's focusing on reducing rural roadway departures. And this is Victoria Beal with the Ohio LTAP Center. I have with me today colleagues Ray Brushart and Dirk Gross, who are going to be your presenters for today's session. I appreciate everyone who's already putting the good morning, hello in the question box to let me know that you found it and you're there. Anyone who hasn't done that yet, if you would just drop us a hi or hello in there, we appreciate it. The other thing is I've taken a little different approach with the handouts for today, and I have already got them uploaded to our website and put out the link to the location in the chat box. Apparently, though, a couple of people who've tried to download the session 5 file found that it isn't downloading properly. So after the webinar today, I will have Ray recreate that and we'll get it re-uploaded. And we'll send out this link as a reminder after everything has been re-uploaded there for the session 5. And I've also got the videos loaded to our YouTube channel. So without further ado, I believe I've covered all of our housekeeping items already too. So Ray, it is all yours.
All right, Victoria. Well, it's the last part of our webinar series for FoRRRwD. And again, I'm Ray Brushart with Ohio LTAP Center. And one of the things they call me is the safety circuit rider. And so where we left off the last time, we were talking about countermeasures that reduce the potential for crashes after the vehicle leaves their lane of travel. And let's see if we can see where we left off. So we talked about shoulder widening, looked at some examples of that. We looked at the pavement edge drop off, which we have a safety edge countermeasure for that we would like, at least in Ohio, for this to be a standard for our 2-lane road resurfacing projects, and how it eliminates or reduces a lot of different types of crashes that we're concerned about in this webinar series. And then we just started talking about the clear zone, and then we defined the clear zone as the unobstructed traversable area provided beyond the edge of the through traveled way for the recovery of errant vehicles. And there we show a picture there on the right of a big tree. And I think I started talking about, in some communities, I mean, you can think of exotic or more exotic states like South Carolina down by Charleston. They have these roads, they have these giant oak trees right up beside the pavement. And of course, they're not going to allow anybody to cut those trees down. But even in Ohio, there's some trees that communities love, and they don't want to have them cut down. But then there's trees that we can cut down and maybe replace, and we can replace them a further distance back from the edge of the traveled way, maybe. But we have some source documents and some guidance about the benefit we get by moving these fixed objects like trees or utility poles and things like that further away from the edge of the traveled way, and not really even that much further away. We get an added benefit from that for reducing the fixed object crashes. And so here we have this table from the Roadside Design Guide from AASHTO, and talks about our different roadways, different design speeds, and different traffic volume levels. And then it talks about the ditches, what's the fore slope grade and the back slope grade. And they give us some guidance about what the design of these ditches should be to help the clear zone, maybe make them a kind of traversable and prevent rollovers and things like that. But what is traversable? And if we take a look at that table a little closer, we would see that if the slope is 1 to 4 or flatter, then yes, it is traversable. And but if it's steeper than 1 to 3, we're saying no, that is not traversable. And then we get into the term recoverable. It's not as good as traversable, but if you go off the road and go into the a 1 to 4 flatter, you can still recover. Recovering means, I guess, get back onto the road without hitting anything. And then we get into critical, and you don't want critical. So 1 to 3 or steeper is that's not good. So that could result in you crash into a steep back slope, or you have a rollover type crash. And so if we take a look at some statistics about rural roadway departure rollover fatalities, and this information comes from the Fatal Accident Reporting System, which is from FHWA. If we look at the years 2014 to 2016, when we look at roads that are greater than or equal to 55 miles per hour, like most of our 2-lane rural roads are, then if you have a rollover, then 78% of the time it's resulted in a fatality. And then a lot of the 44% of these crashes happen in the curves. And you take a look at the different, how they broke this down to different categories: collector and local roads, 2-way undivided roads, and 2-lane roadways. But you can see a very high percentage of these type of crashes result in fatalities. And so this shows why adequate clear zones and traversable slopes are so important. So rollover fatal crashes predominantly occur in rural areas with posted speeds of 50 miles per hour or greater. As you can see, almost half of those occur in the curves. So we begin to see a theme with curves. For such a small percentage of the roadway miles, they are well overrepresented in our crash data. And only about 5% of roadway miles are curve miles. Let's take a look at a rollover crash here. That was a German video clip, at a test facility. So it didn't just roll over once, did it? Rolled over several times. And there was actually, in this test, they actually had a live driver in that vehicle. But of course, they had him strapped in there like a NASCAR car, so he wasn't injured. But as you can see, that's how these crashes happen in the curves. Okay, so let's move on to what happens when we flatten our non-traversable slopes. And here we have a picture there on the right of a roadway in Alabama. And for those movie fans in the house today, this is the location of where the actor Morgan Freeman had a roadway departure crash in August of 2008. And so they extended the clear zone since then. And there is a paved shoulder. And so let me see if we, did I go one too far? There we go. So you see the how they improved it, and then you can kind of see what it was like before. Like this area here, you see how steep it is. So that's how it was when Morgan Freeman had his crash. But since then, they've paved the shoulder and created a more traversable slope there. It was 4.5 to 1, when they filled it and created a slope. So 4.5 to 1, they have this chart, this table over here showing you the crash reductions for single vehicle crashes. So you kind of would expect a higher crash reduction than that, wouldn't you? But it is a crash reduction. And so another treatment we can do in the clear zone is do this treatment with the culverts. A lot of times you see some really dangerous culverts on our 2-lane roads. They're concrete, and they cause a lot of bad crashes. But maybe we can kind of like shave these culverts off, and so that they match the side slope, and the slope should be 3 to 1 or flatter. So they've done some full-scale crash tests, and they have shown that even at low speeds, vehicles can traverse openings up to 30 inches between pipes on side slopes up to 3 to 1. Single pipes up to this 36-inch one we see here can simply be cut to match the side slope. Grading beyond the pipe is also very important and should be made traversable. So that's a treatment that was done in Kansas. But you also see a lot of rural roads have driveways, and they have a ditch alongside them, and the driveways have a pipe under each driveway. And so the picture here shows a treatment for that as well. So if you have the pipes that are parallel to the road and they're greater than 24 inches, then you need to install these pipe runners in there to make them traversable. All right, so it says, what is unobstructed? Tree crashes result in 65% of rural fixed object fatalities. So that's a huge percentage. So, we really need to focus on cutting down these these bad tree crashes. So we have a pie chart here showing that of these different fixed object crashes, of the fatal crashes, 19% of them are trees. Then you also have utility poles, barriers, and other fixed objects. So tree crashes predominantly occur on rural areas, but 1/3 occur in urban areas. Let's see a tree crash test here. So the first one is at, this is kilometers per hour. So the first one's at 50. You can see it go about halfway up the hood, and then 70 kilometers per hour is up to the windshield, and then 90, which is more closer to 55 miles per hour, that puts that tree into the driver's seat. So that's the kind of damage that occurs with a tree crash at different speeds. So you can see the data here from our rural roadway departure tree fatalities. So a lot of this, this is what we can focus on, eliminating these crashes. And, again, especially in the curves. So how can we address corridors with dense trees that are close to the traveled way? We've all seen situations like this. And so it is understood that removing a single tree may be much easier than clearing out a dense forest. But can an incremental increase in the clear zone be achieved? And are there any strategies to keep vehicles on the roadway as well. And so if we take a look at the table on the left, we can see that they've looked at different distances away from the traveled way. So taking a tree and or any obstacle and removing it an additional 3 feet away from where it is, you can cut crashes down by 22%. And it looks at mailboxes, culverts, and signs. I know a lot of county engineers in Ohio, they've come up with policies about mailboxes. A lot of homeowners want the beautiful brick or stone mailbox, and a lot of times they don't even ask, they just build it right there in the right of way. But there's been some policies and things come into place about how to address these situations. Also guardrails and fences or gates, but incrementally moving it away from 3 feet, 5 feet, 8 feet, we get a bigger crash reduction, because we saw at the beginning of this that the 30 feet, if you get objects that are 30 feet away from the traveled way or more, I mean, you're dealing with, you can eliminate 80% of these crashes. And so that's what we're shooting for, because to get things further than that away is impossible most of the time for right of way and things like that. So there is a table here that shows the results of studies and moving objects an incremental distance away. So in this picture on the right, you could take some, maybe not this tree, but maybe the trees up here are closer to the pavement, and then make some decisions about removing them or shielding them, and other methods like delineating them with retroreflective object markers or tape or something. And of course, the other question was, what else can you do in that curve if that's a problem? We've looked at other countermeasures for curves, like adding friction. It doesn't look like there's any chevrons or arrows in that curve, or maybe it doesn't even have an advanced warning sign, things like that. So then we have utility poles. So we have some utility pole strategies. Here we have a picture on the right showing utility poles. They're pretty densely installed there, but there are alternatives. Placing utilities underground, relocate poles further from the roadway, or maybe even decreasing the number of poles. So the NCHRP Report 500, remember I said there was several volumes included in Report 500, but volume 8, as you can see there on the left, is titled A Guide for Reducing Collisions Involving Utility Poles. So they've got some data on utility pole crashes and also some countermeasures included in there. So here we have a nomograph that was found in that Report 500 on page 70. And this nomograph approximates the frequency of vehicle crashes with utility poles. And the nomograph predicts crash frequency as a function of average daily traffic, average pole offset from the roadway, and the density of pole placement, meaning the number of poles per mile. And the nomograph can be used to estimate the effectiveness of proposed countermeasures, such as increasing the average pole offset and reducing the pole placement density. So if we look at the example here, if the base case is if we have a roadway with 10,000 average daily traffic and a pole density of 60 poles per mile, So there's where we shoot across like that. And then the poles are offset at an average of 2 feet. So this is what we're dealing with here with the red. And so this results in 2 utility pole crashes per year per mile. This does not predict severity, but frequency. So if your strategy is to do joint pole usage and the number of poles can be reduced to 20 poles per mile, but maintain the same offset, this drops the crash frequency to 1.2. And then if you also move the poles back to 10 feet offset, the frequency could be brought down to 0.4 crashes per year per mile. So that's how this nomograph works. And then the same prediction model could be used for street trees to predict the effect of offset and density on various average daily traffic facilities. And we'll also be taking a look at another countermeasure that involves breakaway objects, and we'll talk about that in Chapter 6. Another thing about utility poles, they have different types nowadays. They can be energy absorbing or collapsing. Of course, these are not very widely used, but maybe they will be more widely used in the future. Then we have the use of object markers. If we can't provide a clear zone free of obstacles, then we need to look into the use of object markers. And so on the left over here, we have a utility pole that has an object marker on it. And then the trees in the middle here, I think that's in Hawaii. And those trees are very important to the people there. So they're not going to chop them down. So they have placed a solid yellow object marker to delineate those trees. And on the far right, the object marker is always placed at the edge of the hazard zone. And since they have 2 hazard zones here, one on the left, one on the right, we're identifying both of those. So the first harmful hazard is marked with the on the left edge. You can see we have a drop off here, unsafe drop off, and that's what they put there. It's a severe drop off, and then and both sides have culverts. So this one over here is marking a culvert over here. So that's examples of object markers. Okay, so of course I always give some links to where you can find this information and more information on these different countermeasures. So here's 3 links that you can go to on the FHWA Office of Safety. There's one on it's called the Proven Countermeasures page. So there's one on the safety edge, and the other one is the second one here is about the AASHTO roadside design guide and some of the information that we talked about. All that came from in there. You can find it there. And then the other one is the horizontal curves guide. The low-cost treatments for horizontal curve safety, which was published in 2016. Okay, well, let's see if let's do a learning outcome review here. So as far as identifying countermeasures that can reduce the potential for a crash if a vehicle leaves the roadway, what are the countermeasures that we talked about that can reduce the potential for a roadway departure crash? You can, let's have some answers in the question box.
Object markers increase clear zone, cutting trees, removing obstacles, move poles, flatten slope, extending clear zone, gentle side slopes, object clear zones, flattening slopes, rumbles, signage, remove trees, 4-to-1 slope, object markers, larger clear zone, signs, chevrons, delineations, add clear zone.
All right, that's very good. They had widening shoulders, safety edge, center buffer area. I know I got a comment after the last class that this is a luxury that most agencies don't have. I agree with that. But you know, some of our roads might be capable of installing this improvement. And of course, working on a good clear zone alongside the roadway and traversable slopes. So those are our different countermeasures for helping to reduce the crash potential. Okay, so here's a question. Let's see if we can get this right. It has multiple answers. Just put A, B, C, or D. Which of these are true regarding the clear zone? 1, it's an acne medicine. How about that? Or it's the farthest distance a vehicle will go when it runs off the road. Or it is the unobstructed traversable area provided beyond the edge of the through traveled way for the recovery of errant vehicles. Or the clear zone does not extend outside of the right of way. So what do we got here?
A lot of people are picking C, but a few people picked A, B, and D. But the majority are picking C.
All right. Well, A is actually true. See, I got a picture of it there on the right. B is not the case. And then C, that is true. That's the definition of clear zone. And then D is not the case. So the right-of-way does not define the clear zone. It may affect what can be done to address obstacles that are, but some of those are outside of the right-of-way. So sometimes we can't, but we can do what we can with what's in the right-of-way. As far as B goes, that B is false because the clear zone values are based on 80% of vehicles stopping. Okay, let's do a knowledge post test. What improvements were made to reduce the potential for a crash if a driver leaves the roadway in this picture taken from state of Missouri?
Paved shoulder, widening asphalt shoulders, striping, shoulder whitening, center paint, center buffer area, clearing trees, tree removal, guardrail, remove tree, center separation, clear zone, cut trees.
Very good. So yeah, at this location, paved shoulders were added, and there appears to be a bit of an edge drop off that could be mitigated by the safety. Maybe they did not use safety edge like they could have here. There's also a centerline buffer area. The clear zone looks good both before and after, and a tree appears to have been removed from the inside of the curve too. So they removed this tree from the clear zone, and look at how it really opened up the sight distance once it was out of there. Okay, so that's what I have for chapter 5. Do we have any questions on that one, Victoria?
There were 2 that came in. Actually, one was more of a comment early on about cable guardrail. But the one question that did come in says, seems like speed will also affect the frequency. Are there different graphs for different speeds? And I apologize, I didn't catch that one when you were on that exact slide. So maybe we can circle back around to Nicholas at the end and have him refer to which slide he was looking at.
All right.
I know you need to keep going to make sure we get through everything today.
Well, maybe when Dirk gets on here, we'll give him a pop quiz with that one. But it probably is in there. There's more tables and graphs in that resource about that, where I got that graph, than just that one. We just kind of handpick that table. Okay, what else am I doing here? I gotta find my other, this one. Okay, well, let's move on to Chapter 6, where we focus on minimizing the severity of a crash. So we've done all we can do. We tried to keep the car in its lane of travel with different countermeasures, and they left their lane, and we've done our best to give them a recoverable area to try and get them back on the road without crashing. But we've done all we could do, but they still had a crash. And so now we need to look at some countermeasures that minimizes the severity of the crash. So our learning outcomes are going to be that after this session, you will be able to identify crash-worthy sign support systems. I know somebody had a question about barrier cables, so that's going to be in this chapter. You will be able to identify the essential elements of barrier systems, and you'll be able to recognize common installation issues for roadside hardware. So let's do a knowledge pretest. Let's take a look at this picture and tell me if you can identify what might affect the performance of the barriers that are shown here.
Bunch of people putting curb, end treatment, resolution increase for sign legibility, posts and asphalt offset wrong, no end treatment, curb offset bridge, curb, some damage in existing barrier, transition between barrier types, offset from curb, no bridge terminal, damage to the existing guardrail, transition railing, need bridge terminal assembly.
Those are all very good answers. Okay, so this picture was taken in Tacoma, Washington. And so what we see is some old guardrail in the foreground. And it says no block and 12 feet 6-inch post spacing. May not contain the vehicle. The curb is in front of the guardrail. See this curb here? That's a curb. So if your tire gets over that and caught in here, it's just going to guide the car on up to the crash into this end treatment here. So it might cause the vehicle to lift, which would and hit the barrier higher than normal. So if the tire stays on top of it, it's saying it would hit this, or the car would be up higher and do more damage that way. And the guardrail might lead the vehicle into the end of the rigid bridge rail. And the bridge rail, the curb and parapet might cause some instability in a vehicle. So that's what it's saying there. So yeah, obviously there's a problem there, right? So we need to know. So we'll talk about these sort of issues and how to prevent them in this chapter. So again, we're wrapping things up here. We're on the third part of this, of our objectives, and that's to minimize the severity. So one of the things that we're going to be looking at is called MASH, which stands for the Manual for Assessing Safety Hardware. And the second edition was published in 2016. So that's our guidance document for this information. And we'll be looking at breakaway devices and barriers. So our breakaway supports, they reduce severity by providing breakaway hardware, and then we can use these on sign supports, luminaire supports, and utility poles. And if we look at the MUTCD, it requires crash-worthy sign supports on all public roads. It says that in section 2A-19. Maybe we can recall from session 2 the MUTCD requirements for curve signage. Similarly, the MUTCD requires sign supports to be crash-worthy because they are fixed objects with potential to harm the occupants of the vehicles. Crashworthiness is determined by MASH standards, and each vendor or agency is responsible for testing and assurance. Luminaire supports and utility poles comes under AASHTO guidance. Structural supports for highway signs, luminaires, and traffic signals. All that was updated in May of 2013. So let's take a look at some options for crash-worthy installations. So there's 3 methods are allowed for crash worthiness. In the first picture, we see bending or yielding, where the material fails and either bends downwards or yields due to the force of the impact. Slow impacts are generally not sufficient to bend fully or yield completely, but little severity is a part of the crash. Lap splices are generally not practical as a standard, but some states have approved a lap splice, which satisfies criteria of yielding at impact. Height and length of splice in front and back members are critical for performance. No more than 3 posts in a 7-foot circle of 3 or less, and must be breakaway. That's part of the spec. Directly driven or field splices, only 2 in a 7-foot span. Direct burial is acceptable given proper depth, soil type, and structural steel properties. For example, weight per foot. And then in the second picture, we have a slip base, and we can use those for lightweight structural steel, number 3 or less. Let's see here. So that's just the typical breakaway right there. These screws have a shear force. If it's hit at a certain strength, then it breaks, and then it yields. And in the bottom right is the breakaway design, of which there are many, generally a small coupling device or a necked down bolt. So these are the 3 different types of crash-worthy installations that are listed in MASH. So you can go to the MASH guide for more information on those 3. So here's some sign support design considerations. You have to consider the direction of the impact. And it says unidirectional or omnidirectional. If a support is likely to be hit from different directions, an omnidirectional design may be appropriate. Large signs usually have multiple supports. This sign's at a T intersection. The slip base is not oriented for traffic on the main roadway. So here's some more sign support design considerations. Slip bases have torque limits. If they're too tight, they may not slip in an impact. Once the base breaks or releases, the stub should stick up. You don't want the stub to stick up more than 4 inches, or it could snag a vehicle. So here's a drawing of the 4-inch max. So the upright shows a wide flanged post with a lapped joint where the lap is too high. So this is too high here. We get into this a lot with our sign grant for our townships. Then here's some signs with multiple supports. Large signs usually have multiple supports. If the posts of a multiple support structure are within 7 feet, then there's a likelihood that more than one post will be hit in the same event. If posts are within 7 feet of each other, they are only considered crash worthy if they have been crash tested together. Otherwise, the post may act more like a barrier and won't give when a vehicle strikes them. So on the left, we see multiple supports within 7 feet. Some smaller supports may have been tested with the vehicle hitting 2 or more. And in the middle, this appears to be 2 large supports that are within 7 feet. And on the right, we can see that the vehicle, you can see the tracks, the vehicle was able to miss both supports. How about that? Good for him, right? And then here we, for multiple supports, large signs with multiple supports also need to have a breakaway mechanism at the base and a hinge just beneath the sign panel. The hinge is located at least 7 feet above ground level so that a vehicle can travel underneath the sign panel. So keep in mind that this clearance height is measured from the ground level at the post and is different from the MUTCD requirement, where you need at least 5 feet from the top of pavement to the bottom of the sign for legibility. Okay, any questions or comments on those, Victoria?
Yeah, Ray, we do have one question. So they wanted you to elaborate on overlap connections at the ground surface.
Yeah, and this picture on the right, what we're shooting for is you're measuring from the ground 4 inches, and that should be the max. So when this breaks away, if it's more than 4 inches, it has a probability of snagging on the vehicle. And you know, and it even goes with like trees. When you're removing trees alongside the road, even you don't want to leave more than 4 inches of the trunk there because it could snag a vehicle, and it can cause an impact like a crash. So if you have it less than the 4 inches, then they can clear it most likely. But that's in the spec for this type of installation. So then we get into our barrier systems. So barriers are fixed objects that can result in injuries when hit. Who'd have thought? Thought they're supposed to protect us, right? But our barriers, there's a list of them there. Cable barriers, W-beam guardrails, concrete barriers. But the focus for this presentation will be the W-beam guardrail. And so barriers are often a last resort. So we're going to look at parts of barriers, requirements for use and testing, and common problems with installations or in-service barriers and maintenance concerns. If objects or harmful effects cannot otherwise be mitigated by removal, relocating, replaced, made crash-worthy, then a barrier may be the last resort. Barriers will sometimes increase crashes, but the increase is usually the minor variety type or incidental contacts. So as you can see, crashes with barriers result in over 300 fatalities per year. So barriers are systems, and the components need to be compatible and continuous. So the figure here is taken from the roadside design guide, and it shows the different components. So we include the standard sections, terminals, and transitions. So we have our upstream terminal or end treatment. Then we have our standard section, and the transition, and our bridge rail, and then go to another transition standard section, and then the terminal. So that's taken from figure 5-4 from the AASHTO design guide. So the photo that appears shows a location where the guardrail elements are not continuous and each end is exposed. That's this one here. So it says it's important to ensure tension continuity throughout the system. So if we take a look at the MASH guide, again, that's the manual for assessing safety hardware, talks about another requirement of a barrier, and that is the proper in-service demonstration of acceptability or performance for its intended purposes. And so we have our different test vehicles that are involved in testing these barriers. So one is the pickup truck there has been, you see the old one on the left, and then the new pickup, that the test pickup truck on the right. That's a 2270P quad cab pickup. It weighs 5,000 pounds. The quad cab pickup has a higher center of gravity and more closely represents the large SUVs. And then the cars down here, we got here, almost looks like an old Ford Taurus or something. Because the primary variables that are in the crash test criteria are vehicle mass. Most testing is with a small car and a large pickup truck. The speed varies by test level, and the angle of impact. Most testing is done at a 25-degree angle. So we have the table here on the right lists the different test levels and the speeds in the vehicles. And then we have our barrier considerations, which are height, different end treatments. Do they end with a terminal or anchor or a transition? Placement conditions, is it on it for a slope, for grading or curbs, etc. And then the length or length of need of that barrier. Let's take a look at the guardrail height. Let's see here. Let's take we'll go over this and show you a good crash test. So in the early 2000s, the Midwest Roadside Safety Facility, the MWRSF, conducted a study to develop a better performing roadside barrier. That research indicated that the performance of the G4 1S strong steel post guardrail improved when the splices were moved to mid-span. Increasing the blockout depth also improved crash test performance, as did raising the height of the rail from 27 3/4 inches to 31 inches, which reduced the embedment of the post. The MGS represents the combination of these factors. The MGS has also been crash tested with 8-inch blockouts, and the Texas DOT is currently preparing to submit a request for eligibility. Other systems were subsequently developed that also have a 31-inch mounting height. When do you need to raise the guardrail when an overlay has reduced the height? That's a good question. The AASHTO Roadside Design Guide 4th edition states that guardrail that is at least 26.5 inches high after an overlay may remain in place. So that's your line there, so 26.5 inches. That's the lowest we want it after an overlay. Let's take a look at what I'm talking about with a crash test. There's no sound on this video. So the barrier absorbed the crash and redirected the vehicle. So the 31-inch guardrail system has been adopted in most states, and you need to consider raising your W-beam barrier systems with existing top of rail height less than 26.5 inches after, if it's 26.5 inches or less after an overlay project. Let's take a look at these, the guardrail anchors. An anchor is needed on each end of a guardrail to develop the strength of the system. The anchorage is usually part of a terminal or transition and may be all that's needed on the trailing end of one-way roads. So I got another video to show. It shows the function of the anchor with a downstream hit. The anchor includes the cable, connections to the guardrail post, and strut. And let's take a look here. Let's see that again. So it shows the location where the cable anchor may not have been connected at the time of impact and the vehicle was able to pass through the system.
Hey Ray, question that's come in. They wanted to know on the overlap connections, are they considered to be approved breakaway? And maybe this is something that Dirk wants to chime in on.
Well, I'm pretty sure that's how we're telling the townships to install their signs with the overlap. We have two different types of posts that we allow them to use. Like I don't know, I forget what they're called. The U, is it the U or W or something? The box, one's a box, but they overlap. But I'm gonna get a better answer. I'll get a better answer and send it out after this. But we'll get that right from the information that we send out in our the township sign grant package. It has all this information in there as they order their signs and posts and all the different hardware. Okay, so now let's move on to some more about our guardrail anchors. So an anchor is needed on each end of a guardrail to develop the strength of the system. And the anchorage is usually part of a terminal or transition. It may be all that's needed. Okay, I already read that, didn't I? Let me move on to our next. Okay, so there's a picture of this is I-75 in Ohio. How shows how what happens when you hit it that way. That probably wasn't the way it was supposed to happen, was it? That shows This is where it shows the location where the cable anchor may not have been connected at the time of impact and the vehicle was able to pass through the system. So that's the line that goes with this picture. Okay, some more about our guardrail terminal. We have different types. You got the tangent or flared, and energy absorbing versus non-energy absorbing. So a lot of these you see, the new ones are crash absorbing, like the attenuator style. So for a terminal to work properly, the grading around the end is critical. And there are three areas of grading. You have the advanced area here on the far right. This is the area where the vehicle is traveling before impact. It's a flat area that helps reduce instability. Then we have our adjacent area, which is the area around post 1. Flat area reduces instability and provides soil embedment for the anchor. And in the run out area, it's a recoverable, where a recoverable slope is desired. Let's see here. Thought I had some animation there, but so if you can see the soil plates and space under the strut, the grading is not correct. In this case, the anchor may not be able to develop the strength of the system. Because the posts are too high out of the ground, the vehicle may not break off the posts, or they may snag on the stubs. This installation may not work for either purpose for the end treatment. So that is apparently not the way to do it. Then we have our guardrail transitions. They're needed when connecting to a stiffed system, may also be used to reduce the deflection distance. Guardrail transitions are needed when connecting to a stiffed system. And here's some examples of the MASH system. What's shown is a MASH TL-2 transition. The concrete parapet is a 36-inch single slope bridge rail, which is published in the TRR-2377. There are several transitions that have been tested for 31-inch guardrails. The TL3 rail transition at the bottom is part of the FHWA eligibility letter B-187, which is in the NCHRP 350 and in MASH. Then we have our soil support. So AASHTO recommends placement of the barrier at least 2 feet from the hinge point of the slope if the slope is steeper than 1 to 3. If the rail is placed at the hinge point, the system may not work effectively because without adequate soil support, a strong post system will deflect too much and a vehicle could go over the top of the rail. You can use longer posts to counteract the lack of full soil support. You can see the hinge point in the picture here. So So a design with 6-foot posts at the slope break past the MASH testing, but with greater deflection. A design with 8-foot long posts placed beyond the slope break past the MASH testing. The length of barrier. What is the purpose of this barrier? Well, the purpose of this barrier, you would think, was to keep people from going off this cliff, basically, but is the barrier long enough for what it's supposed to be doing? So this barrier is there obviously for that steep slope. The last 12.5 feet of rail will not redirect a vehicle, so a vehicle that hits on the end might still go over the steep slope. So they needed to make it longer here. So there is the AASHTO approach for determining your length of need. So the you can see this picture here showing you the run out length and the edge of the traveled way. In order to hit a roadside feature, a driver has to run off the road at some distance ahead of the feature and at some angle. All we really know about the angle is that it decreases at higher speeds. So the AASHTO design procedure does not specify any encroachment angle. Instead, it uses a run out distance and a lateral offset to the backside of the hazard to determine an appropriate barrier design. The assumption is that a driver will try to bring the vehicle under control and try to return to the roadway. If he or she is behind a barrier, then the only choice is to bring the vehicle to a stop. So the whole process hinges on the run out length, defined as the stopping distance off the pavement. So the run out length, so here's the suggested run out lengths for different design speeds, different average daily traffic. So this table is for run out lengths and is found on page 5-50 in the roadside design guide. Run out length is a function of design speed and traffic volume. You will note that the distances range from 470 feet for high speed, high volume facilities to 70 feet for design speeds of 30 miles per hour and traffic volumes under 1,000 vehicles a day. Some states use lesser distances based on different accident studies. These values are lower from previous versions of the roadside design guide and are based on a study called the Cooper study. And the study that documents the basis for the lower run out lengths went back to 1984 in a study called Guardrail Run Out Lengths Revisited. Another way to calculate is a method called the similar triangles calculation. And the AASHTO design process is really calculating one side of similar triangles using proportions. The field check method would be to pace or measure the run out length from the obstacle and look back to the obstacle. If the guardrail is intersecting the sight line, it is probably long enough. So there's a run out length for a design speed of 60 miles per hour and average annual daily traffic of 8,000. And you come up with a run out length of 250 feet for an object that's 30 feet off the roadway. There you can see how they did their calculations. So if you adjusted this from 30 feet to 20 feet here, then you could use the similar triangles to come up with the new run out length would be 168 feet. Here's a graphic showing that if a barrier designed on horizontal curves can be done graphically, it can also be done for tangent section. First, we define the hazard Next, measure upstream a distance, LR, from the hazard along the edge of traveled way. Then define an envelope of protection from the end of the runout length to the back of the upstream face of the hazard. Now, various designs using different barrier offsets and flare rates can be drawn to intercept the envelope. And then on the curve here, we see if the obstacle is on the outside of a horizontal curve, the length of need is defined by a tangent from the obstacle to the edge of the traveled way. This is best determined graphically. So there you have your So we're drawing this straight line from the curve. If the car went straight, didn't make the curve, then the placement of the guardrail is in this area here. But we have to use caution since guardrail terminals pose a greater risk than a standard run. And since many roadway departure happen on curves, it may be more desirable to extend the guardrail around the curve in some cases. So you can see here. So if we take a look at this picture, what is the best terminal for this location? So we have a big side slope here that goes up from the edge of the traveled way. And the guardrail, they have an
Right, some
object
people,
marker here.
and they're commenting buried and back slope could be used, bury the end in their back slope, buried, embedded.
Yeah, because definitely something needs to be done, right? Because
One person did say no, should be extended further.
let's see here. So BIB, buried in, what was it? What was the first few answers there?
Embedded, buried in back slope.
Yeah, buried in back slope may have been more appropriate here. Either way, the barrier appears to be too short to keep a vehicle from getting to the steep slope back in here. And so there is a catalog of end treatments that you can find if you go to the FHWA Office of Safety and then go to Roadway Departure Countermeasures, and then they have road terminals. And it's got, like I said, a catalog of different end treatments, but the buried in the back slope would be definitely better than what's there in the picture. How about this one? Was this the best place to end this guardrail? And is this barrier long enough? And could it have been terminated at a different location? Got another picture of it here too. Looking at it from the other way. All right, so I need to speed up here so I give enough time for Dirk. But the right photo shows that it definitely has an inadequate length of need. A vehicle could easily pass behind the rail and hit the trees or the slope. It also didn't have the advanced or adjacent grading. And the photo on the left shows that if the barrier had been a little longer, a flatter slope would have been encountered. Okay, so as usual, I know we have to pass quickly through these different treatments, but we do provide to you the documents that this information comes from. So it's in your handouts, and you can see we have different resources here from the FHWA Office of Safety on the different roadway departure countermeasures. Under reducing crash severity, we've got the median barriers and a roadside design guide that you can view and download. So let's see what our learning outcomes, what they did for us today. So which of the following is a type of crash-worthy sign support system? Base bending, floating sign system, slip base, breakaway.
We've got C, D, A, C, D, C, D, A, all, A, C,
All
D,
right.
A, B, D.
All right, very good. It's A, C, and D. We haven't invented the floating sign system yet, but we wish we did, didn't we? So very good. And what are the components of a barrier system? I think I need to go quickly through these so I give time for Dirk. So
Okay.
the different barrier systems include standard sections, terminals, and transitions. And which of these are common installation issues that could affect the performance of the guardrail? Length, placement near slopes, inadequate terminal grading, or the color of the rail that does not fit the environment. Okay, so it's the first three. The color of the rail may be an issue in some areas like national parks, but it would not affect the performance. Okay, then for our post-test, we go back to our first picture in this chapter. So what improvements do you think will reduce the severity of crashes for this location? Again, I want to make sure that Dirk has time, so I'm just going to go what they did here. As you can see on the right, when they improved it, they updated the guardrail. They placed the guardrail over the curb. A transition was installed between the approach guardrail and the bridge rail was retrofitted. So that was the treatment there. So that's all I have for our chapter 6, and that's all of our technical information for this webinar. And I'm going to switch over now to Mr. Dirk Gross. He's our District 6 planning engineer, and he's on the our district safety review team. And he's got a project he wanted to share with you guys that involved some of these FoRRRwD countermeasures here in Central Ohio. So Dirk, you could take it away.
All right. Can you see my screen here?
Yes, you can enlarge it. You can enlarge it. You got a full screen?
It looks fine. Yeah, his is full screen. Looks good. Thanks.
Okay, good. Okay, so the presentation's up. I was asked to give an example of a safety project that we did that involved run off the road type crashes. And so I put together this presentation. Let's see. So a little background on me, I'm Dirk Gross. I work at ODOT District 6. I've been with ODOT for 33 years. Primarily I was in central office roadway engineering. I ended up being the administrator there for about 10 years. Since 2012, I've been in District 6, and one of my responsibilities is managing the District 6 safety program. So we had a project, or actually had an issue that came up on Route 62. 62s in US 62s in Northeast Franklin County between New Albany and Johnstown. It's 55-mile-an-hour 2-lane highway, has about 14,000 ADT. It's 11-foot lanes and about 2 to 3 foot shoulders. We had a customer complaint in October 2015, about several crashes that had happened near one of the curves. And so the District 6 safety group went together and did a crash analysis that covered an area from Walnut Street to the Licking County line, which is kind of shown on the screen there in that highlighted color. Come on, there we go. So this is the area that we were looking at. Tippett Road up there is about the Licking County line, Walnut Street's at the bottom, and so we looked at that whole stretch of roadway. There's 3 curves in that section of roadway, which from south to north we'll identify as curve 1, 2, and 3. And the crash analysis, or the results that we did for a time period from January 2012 to November 2015, you can see on the left side of the screen there. So we had 25 total crashes in the area, 15 northbound, 10 southbound. Curve 1 had 4 of the crashes, 3 of those were northbound, 1 southbound. Curve 2 had 5 crashes, all 5 of those were northbound. Curve 3 had 4 crashes, and they were all southbound. Most of the curve crashes are wetter snow conditions, and most of the injuries were in the curves 1 and 2. The segments outside the curves accounted for 12 crashes, 7 northbound and 5 southbound, and most of those were run off the road or had illegal passing or some kind of a passing related crash. So in this area there were several, Franklin County Sheriff put together this accounting of some of the fatal crashes that had happened out there in this particular area. The picture on the left is the one that caused the calls and the questions to us about the safety out there. That was in late November 2015. One of the cars was reported to be going about 60 miles an hour through that center curve and hit another car, and there was a fatality. There was a fatality to the north on the tangent section. It was really just an equipment failure. The vehicle lost its wheel and went off the road and in the ditch and struck a pole. And there's a couple other fatal crashes too in that area. So we did a field review, went out and drove through the project, and this is a picture of curve 1. This is going northbound from Walnut Street to the north. So curve 1, it had the curve warning sign, advisory speed 35 miles an hour, and had chevrons. Curve 2, I have a couple pictures of this. This is again on the south side. It just so happened that when we were doing the field review, there was had been another recent crash that had someone run off the road and taken out the advisory, the curve warning sign for the curve 1. And so this curve also had 35 mile an hour advisory speed and chevrons installed. There was also, there's a utility pole you can see on the left side there that's fairly close to the inside of the curve. There's also driveways for some residences along there. We looked to see if drainage could have been an issue, see if water was ponding out onto the roadway, but we had the garage folks got there taking a look. They never really found any evidence of water coming out on the roadway, so there wasn't any standing water issues as far as we could tell. So we didn't address any drainage issues there. So curve 3, that's the north curve, and this is looking southbound. That also had a curve warning sign, advisory speed 45 miles an hour, but there's no chevrons installed on that particular curve. So Franklin County Sheriff had a speed trailer they put out there between curves 2 and 3, and this is the results they had out there. They had a battery problem with it, so the trailer didn't really run much during the dark times, but during the daylight hours when it was actually functioning, they had an 85th percentile speed of about 54 miles an hour, which is really, not bad. It's 55 miles an hour. They had about 7% of the vehicles were speeding out there. They had a maximum speed of 72. So we got together with Tech Services to have them go out and do some skid tests, and they got out there. All this happened in November, in December, right after the November crash. So Tech Services was able to get out there on early December, and their testing came back. They found that the polishing of aggregate was looking like it was a problem. And you can see some of the pavement information. It was resurfaced previously in 2005, and we had an upcoming project coming up that was going to be built or done in fall 2017. So the field review summary, the curves were inappropriately signed. With the ball bank indications, we came out. Curve 1 should have been a 45-mile-an-hour advisory speed. Curve 2 was correct at 35. Curve 3 was ball banked out to 50 miles an hour. There was also no chevrons for curve 3, which for the current advisory, it's 10 miles an hour less. It's just an optional, but they weren't there. Most of the curves had possible contributing factors of insufficient friction, and the speeds were somewhat high, and there was illegal or unsafe passing that was a contributor to some of the tangent sections. So our recommended countermeasures. One second here. I'm trying to go between two screens here at the same time. So our short-term countermeasures were correcting the signing, changing the advisory or with the advisory speed, chevrons, oversized signs. We're going to do fine milling for short term for all 3 of the curves. We were working with Franklin County Sheriff for enforcement. They did a week-long enforcement blitz. There was also a message board that was put up to the south of this section advising people about safety. Medium term, we were looking to see if we could do something for the friction on curve 2. We were considering high friction treatment, but we ended up coming out with microsurfacing as the recommended solution. Also centerline rumble stripes, 6-inch edge lines. That was, I think, prior to our standard 6-inch edge lines we're doing systematically now, but we went with 6-inch lines. And then for long term, just to monitor the crash data to see if those improvements had helped out. So again, with the signing, for the curve 1, it was originally signed 35 miles an hour. We went to 45, so we actually raised the advisory speed to match it to the ball bank. Curve 2, that was 35 miles an hour, and we retained 35, but we went with oversized. Curve 3 was signed for 45, and we raised the advisory speed to 50 miles an hour. And we also placed some oversized chevrons on curve 3, which are an optional per the OEME TCD. And that work was completed in January 2016. So the fine milling was completed in January 2016. It was a joint thing between BOCA, who went out and did the milling, and our ODOT garage. Went out there with ODOT equipment and did the maintenance of traffic and removal of material and the rest of the work. So it was sort of a combination between the contractor and ODOT crews to get that work done. Then there was the enforcement. When the sheriff was out there, they for about a week, they had about 165 stops. Some citations, most of what they had was warnings. They had 133 warnings. And then we also had the portable message board set up from December and 15 through beginning of January. So the medium-term countermeasures, there's a lot on the screen, but basically this is what's in the scope. So this covered all the medium-term things we talked about. There's a plan note down there on the bottom, that item 421, the microsurfacing. the main point that comes out of that was that they used a specific aggregate for the microsurface just through that curve with trap rock and limestone. So that was the high friction, or the friction countermeasure that we were doing versus, let's say, high friction treatment where you apply that on the surface of the pavement. So this is just, the makeup of the pavement itself. And also this project installed the centerline rumble stripe and the 6-inch edge line. So the before and after crashes, you can see on the top there's 44 crashes and the different crash types. On the crash summary sheet there on the left, you can see the years. So the years 2013, 14, and 15, those were prior to any work going on out there. 2016, we had implemented most of the short-term countermeasures by the end of January 2016. And those were in effect out through September 2017. And then from September 2017 to current, the medium term, which was the rumble stripe and the overlay, or the microsurfacing was done. So you can see there was a significant drop in the crashes during that time. There was let's see, I got, so there's no fatal, of all the injury type crashes, there was been no injuries, no fatalities that happened out there. It's been a significant reduction in all the crash numbers. They are down at about, I think we had about 8 crashes a year prior. Now we have like 4.25 crashes. And so it seems to have been very effective. You can see it keeps declining there on the right side. Yeah, so that's the summary sheet. It's a little different than the handout, but that's a picture in the background I put up for the showing what the final looks like. That's the centerline rumble stripes. The pavement doesn't look any different through the curve. It looks exactly the same as coming in on the approaches. So you can't really tell there's anything there. We were kind of concerned that the locals might think that, after the resurface, we didn't do anything, because after the milling, they would have seen some, the milling effects on the pavement, and this doesn't show anything there, but it's been effective, and so it's worked pretty well. And finally, this is just acknowledgement. There was a lot of people, a lot of groups that got together to do all this work, especially in the time frames that we did this. I mean, we had the first complaint in the beginning of December, and by mid-January, we had milled the pavement, done the studies, done the sign, installed the signing, and so then also done the enforcement blitz, and then working on the other plans, doing the final. So there's a lot of people that came together to put this, make this an emphasis, and ultimately ended up being a pretty good project, and it's lasted pretty well. So with that, that's completes my presentation.
Dirk, thank you so much for the application portion of what everybody's been learning through these 4 webinars. It's great to see how that, those types of treatments and this information that we've shared has really helped make a difference in a specific roadway. And I'm hopeful, as I know Ray is and you are as well, that everybody who's been on this webinar series will be able to take this information and have similar success stories in on their roadways. So I do want to be respectful of everybody's time. We are right up against 11:30, which is when we said the webinar would be ending. So I know, Dirk, that yourself and Ray, you'd be happy to still take some questions, but I don't want people to feel that they would have to stay. We'll still make sure you get the certificates and the full credit for the course. And thank you for the comments that are coming in the chat box about the webinar series. We're glad that it has been good information for you. There was one question that came in early on that I'll put out there. It says, what do you do when the hazard distance is infinite? For example, a deep ravine extending 200 feet. And I would take it that this is the, more of the getting them back on the road or trying to minimize the impact if they do run off the road. So, Ray and Dirk, maybe you guys can take this question. We'll see if any other ones come in.
Well, you could think about bundling some of these, of these countermeasures, from keeping people in their lane and with signage and pavement markings and rumbles, and if we're talking about some steep cliff, that's a really long steep cliff, sounds like guardrail is something to consider as well.
Yeah, that's come up a few times. There's I know up just around where I live, there's quarries that have, a vertical cliff. It's outside the right of way, but there's a vertical cliff right there. And we've also had developers who have gone out and put, let's say, a detention ponds out on the front outside the right of way again, but and probably even outside the clear zone. But they're like 2-to-1 slopes into that standing water. And if someone goes off the road beyond the clear zone and goes in, then that's a pretty hazardous thing. So I think you have to look at it and just make an engineering judgment. One of the things is when we had the detention ponds, the developer came and said they thought that ODOT should put up guardrail to protect that. And our response back was, the pond's on your property. If you're concerned about people going into the pond, then maybe you should put up the barrier on your property. And that ended up what happened. And that's also happened on quarries. And the quarries go out and they put ones I've seen where they don't have embankments, they have put barrier guardrail or something like that on their property. So if they don't do something like that, then as a public official, you're going to have to make the determination: is it worth the impact on the public by having the barrier there, or someone running off the road? Technically, we may not be liable for it, but it's still a significant injury if they hit that. So you can put them. Technically, the barrier is supposed to be up close to the road. You could potentially put the barrier out to the outside, but if you do, you're going to have to make sure that the slopes and all the grading and all that is appropriate for that location, because the guardrail is not really designed to be hit 30 feet off the road. So those are tricky questions, but you just have to kind of look at every one of those case by case.
Right. So we went over
from that same individual. I'm sorry, Ray. Let me read off this other question.
All right, go ahead.
Sorry. It says, how do you compute the length of need for an infinite hazard distance?
Oh, computing the length of need? Yeah, I'll defer to Ray.
Well, the AASHTO design guide is going to have give you some help. That I shared with you that resource, but you're obviously going to have to sit down with an engineer and talk about that, take a look at it. And we have our own section at ODOT that we have our own guardrail specialists. You can always start with our district. What department is that at District 6 that talks about guardrail, Dirk?
Our plan design section typically.
So you can begin your the answer to your question process by starting with your district contact there in that office.
Yeah, we have designers that specialize in guardrail and calculating out the length of need. So,
and then you have your county engineer. Who owns the road? Is it a county road, a township, or state? And start with the agency that owns the road first, and then go from there. And then if it's not ODOT, then you can always contact ODOT for assistance.
Yep. Well, thank you both very much. There's no other questions right now. And is there anything else you guys would like to add before I push the button to end it for everybody?
No, I think I've got all I needed.
Okay.
Well, just yeah, we showed you in the first session all the statistics that show all the the big percentage of fatal crashes that happen on rural roads, and if we can focus on lowering the number of curve crashes, and then the three other main types of crashes, which is rollovers, trees, and head-on, and of course most of those happen in curves. Use these low-cost countermeasures, and we're going to see a big reduction in roadway departure crashes. So focus on implementing these and even bundling some, since they're low cost, with your other projects you have going on.
Yep, it'll help us get to 0 deaths. All right, everyone, stay safe and have a great rest of your day. Thank you.
All right. Bye-bye.
Bye-bye.